Have you ever been scrolling around a 3D map on your phone and just stopped to wonder, how does it actually know? How does it know how tall that mountain is or how deep that valley goes? Well, today we're going to pull back the curtain on the incredible science that turns a bunch of flat pictures into those amazing 3D worlds we use every single day. So where does this all begin? It starts way up there, in the sky. You've got a specially equipped plane flying in these super precise straight lines. And as it goes, it's just snapping picture after picture after picture of the ground below. Now, the key thing here is that the photos overlap. That's going to be huge later. But for now, they're just what they look like. Simple, flat, 2D images. And right away, that brings us to the big mystery, right? If all you have are flat photos, how on earth do you pull out the third dimension? How do you measure the height of a skyscraper from a picture that has absolutely no depth?
Well, you guessed it, it's not magic. It's actually a brilliant field of science. So let's dive into the core principles that let us build a 3D world from what are essentially 2D pixels.
The official name for this whole process is photogrammetry, and it's exactly what it sounds like. Photo measurement. It's the science of taking incredibly precise measurements from photographs. We're not just looking at a pretty picture. We're treating that photo like it's a treasure map filled with geometric data. So here's where you have to kind of flip your thinking. An aerial photo isn't just art. It's a precise mathematical projection of the three-dimensional ground onto a two-dimensional surface. Every single pixel in that photo corresponds to a real point on Earth. Now, this whole thing would be pretty simple if the Earth was, flat as a pancake. But of course, it isn't. You've got mountains and valleys and buildings, and all that topography creates a really interesting effect in the photos, a kind of distortion. And this is where the real genius of photogrammetry comes in. The secret to measuring height isn't found in the parts of the photo that are perfectly to scale. No, the secret is actually hidden inside these so-called errors or distortions. This critical distortion has a name: relief displacement. And it's the hero of our story today. Basically, in any aerial photo taken straight down, any object that has height, a tree, a building, a mountain peak, will look like it's leaning away from the very center of the picture. This isn't a mistake or a flaw in the camera, it's a predictable geometric effect. And it's the key to everything. This slide shows the idea perfectly. Look at the real-world points, capital A and capital B, on the ground. Because they're at different heights, when you look at them on the flat photograph, their positions, little a and little b, get shifted outward. That shift, that little bit of movement, that's the relief displacement we're talking about. Okay, let's break down the geometry just a little bit. Don't worry, it's pretty straightforward. The camera up at point O sees the bottom of the tower at A0 and the top at A. On the photo itself, the base gets recorded at point A0, but because the top is higher up, the light from it travels at a different angle, and it gets recorded further from the center, at point A. That measurable distance right there between A and A0, that's the displacement we can actually measure on the photo. So, for a long, long time, this displacement was seen as a problem, a real headache you had to correct for. But then, some very clever engineers had a realization. This problem? It wasn't a problem at all. It was the solution they'd been looking for the whole time. And here it is. This is the big aha moment. That displacement, that leaning effect, it isn't random. It is directly proportional to the object's height. A really tall skyscraper will lean a lot more in the photo than a short little shed. The so-called error actually contains the exact data we need. And of course, there's a little math to back it all up. Now don't worry, you don't need to memorize these formulas, but what they do is pretty amazing. They let an engineer take things they already know, like how high the plane was flying, and combine that with the amount of lean they measure on the photo, and then solve for the one thing they don't know, the object's real height. We're essentially working backward from the distortion to find the height that caused it in the first place. Okay, theory is great, but let's see this thing in action. Here's a real-world example. We've got one photo and 2 points on it, A and B. We already know their true elevations. Point A is higher up than point B. The challenge is, can we figure out the actual real-world distance between them on the ground, not just the messed-up distance on the photo? So here's the trick. We have to correct each point one by one. Since A is higher than B, it's going to be more distorted in the picture. So first, we plug point A's info into our formula, telling it that A has an elevation of 500 meters. That spits out its true ground coordinates. Then we do the exact same thing for point B, but we use its 300-meter elevation. We're basically undistorting the image, one point at a time, to find out where they really are. And once we have the true corrected ground coordinates for both A and B, we can just do a simple calculation to find the distance between them. And the results? Boom! 545 meters. By treating that flaw in the photo as a piece of data, we calculated a precise, real-world distance. It actually works.
Okay, so that's awesome. We can find the height of one point or the distance between two, but how do we get from a few calculated points to a full, rich, beautiful topographic map? What's the big payoff here?
Well, the answer is scale. Modern systems don't do this for 1 or 2 points. They do it for millions of points, creating this massive point cloud, which is basically a complete 3D model of the ground. But that creates a new challenge. How do you show all that amazing 3D information on a flat, 2D map?
The classic, and honestly most elegant solution is the contour line. A contour line is really simple. It's just a line on a map that connects all the points that have the exact same elevation. You can think of it like the shoreline of a lake if the water level rose in perfect 10-foot steps. Each shoreline would be a contour line.
And this visual just makes it all click, doesn't it? On the left, you see a mountain from the side with these slices at different elevations. On the right, you see what that looks like from above on a map. Each of those slices becomes one of those closed loops, a contour line. Just by looking at those lines, you can literally see the three-dimensional shape of the mountain on a totally flat surface. And reading these maps becomes really intuitive once you know the basic rules. If the lines are packed super close together, it means the elevation is changing fast. That's a steep hill. If they're spread way out, it's a nice gentle slope. If you see loops with the numbers getting higher as you go to the middle, you're looking at a hill or a mountain. And if the numbers get lower, you found a depression or a basin. This comparison makes it crystal clear. The hill on the left, the contour lines are going up towards the center, 80 is inside 70. The depression on the right is the total opposite. The values are going down towards the center, 60 is inside 70. It's like a simple, powerful language for describing the shape of the land.
And this right here is the final product, a detailed, information-rich topographic map. Every single winding line on this page tells you a story about the land. Its ups, its downs, its cliffs, its valleys. It reveals the true shape of the Earth. And it all started with a plane, a camera, and the brilliant idea that a flaw in a photo was actually the key to unlocking the third dimension.
So I guess the big takeaway is this. Sometimes the most important information isn't in perfection, it's hidden in the flaws. So the next time you're panning across a mountain range on a digital map, maybe you'll see not just the pixels, but the beautiful, perfect distortion that made it all possible.